Okay, let's prove f of g is equal to d by contradiction. So suppose w in d such that w does not belong to the image. Okay? Then we compose it with that phi w. Then the function f of z minus w over 1 minus w bar f of z. This is a composition. Remember, last time we just recalled here, this one, phi w, phi sub w of z. This is a composition of a phi sub w composed with f of z. Okay, this is analytic in G and never vanishes. Because it vanishes if fz is equal to w, but fz is not equal to w, so it never vanishes. Okay, we have a non-vanishing function. Then by hypothesis, there is an analytic function h from G to C such that h of z square is equal to this composite function. So is equal to f of z minus w over 1 minus w bar f of z. Okay. So it has square root, analytic square root. Phi w is a Mobius transformation, right? It's a Mobius transformation. So this phi w circle f of z, it maps G to D. So you compose this f, technically it's from D to D. So this is f, this is a phi w. But anyway, the composite function is from G to D. You take square root, h maps G also to D. Okay, h is also a function from G to D, analytic. It's a square root of a function, a number, a complex number with modulus less than 1 also has modulus less than 1. Okay, then define, we're going to construct some, create a function g from domain G to C by g of z is equal to h prime of a over h of a, h prime of a, and times h of z minus h of a over 1 minus h of a bar h of z. Okay. Okay, then this g of z belongs to D. It's again the Mobius transformation. Check here, it's again the Mobius transformation with a rotation. This is a rotation. The Mobius transformation with a rotation. So it's what it is. It is actually some constant c times, this is a phi h of a compose h of z. Okay, phi sub h of a compose h of z. H of z maps G to D, then by this composition is still inside D, and the C is a scalar multiplication, rotation. This you divide by the modulus, it's a rotation. So Gauss value of C is equal to 1. So G maps G in D, G of A is equal to 0. and G is 1 to 1. G is 1 to 1. Why G is 1 to 1? H is 1 to 1. Why H is 1 to 1? H is the square root of a 1 to 1 function. Okay, so F is 1 to 1, composed with phi W is also 1 to 1. So this composite function is 1 to 1. Then H squared is a 1 to 1 function, then H has to be 1 to 1. H is 1 to 1, you compose it with phi. Okay, so because here it say the author put a y, a question mark. So let's see, 1 to 1. From F, you go to phi W, compose F, and then you get H, that's the chain, H, and then from H you get this G of Z. So that's the chain Y G of Z is a 1 to 1 function. Whenever you compose 1 to 1 function with a phi A, it's still 1 to 1 function. Okay. Okay, so next, let's compute the G prime of A. We already have the domain, the range inside the D. GA is 0, G is 1 to 1, G is analytic, of course, and we want to compute G prime of A. G prime of A, of course, this part is constant. H prime of A over H prime of A. Well, numerator has opposite value. And this part, you apply the quotient rule, whatever rule you do it, it's calculus. And then you evaluate at A, you get H prime of A times 1 minus opposite value of H of A squared over 1 minus H of A squared, and then square the quotient rule. All right, and then you, after cancellation, you cancel many terms, you will get H prime of A opposite value over 1 minus H of A squared. Okay, this is it. Then we are going to evaluate. We are going to try to estimate it. Basically, we are going to show that the G prime of A is greater than F prime of A. Then we get contradiction. How do we have it? How do we have it? Okay, now let's see. H of A squared. What is H of A squared? H of A squared is F of A minus W over 1 minus W bar F of A. F of A is 0. We know F of A is 0, so it is equal to negative W. It is negative W. So we have opposite value H of A squared is equal to opposite value of negative W. It is opposite value of W. W is a point outside of F of G. All right, W is a point outside F of G, and then we need H prime of A. H prime of A, we're going to use this formula. We differentiate. This is called, in the book it is called 4.6. We differentiate 4.6. Then we have the left hand side is just a 2H of A and evaluate at A. 2H of A, H prime of A. Right hand side, you do that computation, it is equal to F prime of A times 1 minus square. So I'm not going to do it again, you just try it and remember that FA is equal to 0. FA is equal to 0, so you may not see the denominator. Okay, you will not see the denominator because 1A is equal to 1Z is equal to A, FA is 0, W bar times 0 is 0, so the denominator is just 1, always 1. So that's the advantage of this formula. Okay, So what we get? We get g prime of a. G prime of a, remember it's ups value, h prime of a over 1 minus h of a ups value squared. So this is, what is this? We're going to put f prime of a 1 minus w norm square over 2h of a. This is f prime of a, and put ups value. Be careful, you only need to put ups value here. F prime of a is positive. This is a positive number. 2 is a positive number, so you don't need ups value. You only need to get ups value of h of a. H of a is negative w. And over 1 minus norm of w square. Right? 1 minus norm of w square. No, not square, just w. 1 minus w. Here, there's no square. Okay, so let's simplify it. What we have? We have f prime of a. 1 minus w squared, 1 minus w, you cancel them, you get a 1 plus norm of w. 2, ups value of a, fa, ups value of h of a is square root of ups value of w. Right? So you take square root, you get this. And the w is inside the d, then 1 plus ups value of w is always strictly greater than 2 times square root of ups value of w. It's inside, it's not equal to 1. If it is equal to 1, the norm is equal to 1, then you have equality. If the norm is not equal to 1, there's always inequality. So it's always strictly greater than f prime of a. See, it is strictly greater than f prime of a. Okay, this gives the contradiction about the maximality of f prime of a. This contradicts to the selection of f. We require f prime of a is greater than or equal to any other g prime of a. But here is a contradiction. This contradiction comes from the existence of w. If w does not exist, then this whole construction cannot work out. Hence, fg must be equal to d. So we do cover the whole open unit disk. See? Okay, so the construction of this G is very constructive, right? It's an intelligent constructive. So you just memorize it and see that's one of a possible choice in your future study. We don't expect every time you create some very creative idea, but once you already know some creative idea, you should be able to use it in your study, okay? So now we already finished one part of our job. We show that if 4.4 and 4.5 are satisfied, then we do claim that existence of f. And now let's establish 4.4 and 4.5. We show 4.4 and 4.5. How do we show it? Remember that we always exclude G. C. G is not C, so we choose B in the complement of G. The complement G. And define G of Z square equal to Z minus B. Again, Z minus B is a non-vanishing one-to-one, a non-vanishing function, analytic function, so it has square root. So we define the the analytic function g, where g from G to C is analytic. So once again, we use that property. We use that every non-vanishing function has analytic square root. Okay. Okay, so I mentioned before the z minus b is 1 to 1, then its square root is 1 to 1. So here, if z1, z2 in G and g of z1 is not just g of z2, it's a plus or minus g of z2, then you will get gz1 square is equal to gz2 square. They are both equal to z1 minus b, z2 minus b. So z1 is equal to z2. So this is actually, I mean, this condition is stronger than the one-to-one. It's not equivalent to one, it's stronger than it. It's not just equal to positive g of z2, it cannot equal to the negative g of z2 also. So in particular, that's why it says in particular, g is a one-to-one. So we have a one-to-one function, analytic one-to-one. All right, analytic one-to-one. Analytic function is always a open map. So by the open mapping theorem, there is a radius, a number r, a radius greater than 0, such that g of a with radius r, this ball, open ball, is contained in g of g. This is open set. Open set, you always, every point is an interior point. Okay. Every point becomes an interior point. Okay, so you have g of a, then you will have, let's put it in the system, negative g of a. Negative g of a. Okay, so we're going to claim actually this negative g of a does not belong to g of a. Okay, why? So if there is a point z in G such that G of z belong to the ball centered at negative G of a with radius r. So we also draw a similar disk. If something is here, then what we mean? We mean the distance between G of z and the negative G of a is less than r, the distance. Okay, so this is a G of z minus plus G of a less than r, equivalent, and it's equivalent to negative G of z minus G of a is less than r. So what we get? We get negative G of z belong to the ball centered at G of a with radius r. This point, negative G of z will have an image in this part, right? Here is the point. You have an image. You have an image, then negative G of z is equal to G of w for some W in G, for some W in G. Right? It's in the this is in the F, not F, G over G. It's in the G of G. It's in the image set, so it's target. And again, remember that we get this implies that here, this one. This implies that Z is equal to W. Z is equal to W. Z is equal to W. This G, Z, G, W, the same thing. It implies G over Z is equal to 0. G of Z is equal to 0, then what's going on? GZ of square is Z minus B. It is 0, then implies Z minus B is equal to 0. Z is equal to B. B belongs to the region G. That's a contradiction. B does not belong to G. B does not belong to G. Okay? This contradiction tells us there's no point inside this ball. Hence, this open ball centered at a negative G of A with radius R intersect F of G, not F, G of G, intersect G of G, empty. It's totally outside it. Okay, this is an empty intersection. Empty intersection. Let's call this U. They said that we call it U. We call it U, then U is an open disk. We take the closure, it becomes closed disk, and then there's the exterior part. Exterior part is also a closed disk in the C infinity sense. Then you have the Mobius transformation. There is a Mobius transformation. There's a Mobius transformation T such that T maps the exterior part of a U closure to D, to the open disk. It's actually I maps open disk to open disk. This is an open unit disk. Okay? So why it maps the complement? Because G of G is here. This is U, exterior part. So it covers all the image of a G. So let G1 be T circle G. See, G maps it to C, and then T maps this part of the image. Okay, let me write it. G of G. G of G is a subset of C. And C infinity remove closure of U. It contains C remove the closure of U and maps it to D by T. This is a one-to-one Mobius transformation. All right, so that's the composition. So we have G1 is analytic and G1 maps G to D. Okay, we do crash this G to D. We crash G to D. That's very good. And this G1 has to be one-to-one. This G1 has to be one-to-one. G is one-to-one. G originally is one-to-one, and the Mobius transformation is a 1-to-1, so this has to be 1-to-1. And now let's see the normalization condition. So let alpha be G1 of A. Alpha G1 of A. Define G2 of Z to be phi alpha. This is alpha. Okay? Phi alpha compose G1 of Z. Phi alpha compose G1 of Z. Then G2 maps G to D again, and G2 is analytic, and G2 of A is equal to 0. G2 of A is equal to 0 because it's G1A is alpha, then this phi alpha maps alpha to 0. Remember that, let me write it here. Phi A is always Z minus A, 1 minus A bar Z. So phi A of A is always 0. Right? So that's a very nice tool. Okay, so again, G1 is on 1-to-1, G2 is 1-to-1, and a 1-to-1. And the problem is we have all the conditions. Let's see what condition we need. We have a long list of the conditions. Okay, check here. We have a long list of conditions. F is 1-to-1, it's checked. Fa is 0, it's checked. Fg is contained in D, it's checked. Analytic, of course, H of G. The only thing is F prime of A is positive. Oh, well. So G2 of A is positive or not? Okay, so we find, well, just a rotation. Find a complex number C, ops value of C is equal to 1, such that G3 of Z is equal to C times G2 of Z has positive derivative at Z equal to A. Okay, so G prime of A is equal to C times G2 prime of A. You want it to make it to be positive, then you just let C be the argument, negative argument, right? Negative argument. C is exponential negative ARG of G2 prime of A. Negative argument times says you change the argument to be 0, then you will have a positive. Okay. Okay, so that's not a difficult part. Then we do construct G3. G3 belongs to F. F is non-empty. So that is a 4.4. We proved 4.4. 4.4 says F is non-empty. We do have this construction. Okay, so let's review what we did. Let's review what we did. So first, this set G is not whole complex plane, so we find a point outside and use Z minus B. And from here we get this G, and G is analytic square root of Z minus B, and G is a 1-to-1. GZ1 is not equal to plus minus GZ2 if Z1 is not equal to Z2. Okay? And from GZ1, G, and we prove that outside of this the image, there is an open disk. So basically we use with the property that outside of the image there is an open disk. And for this open disk, you use a transformation to map the exterior part. This exterior part of the closed disk contains this G. image of G. The exterior part maps the exterior part to the unit disk. Okay, maps the exterior part of the unit disk. So that's a way we map the whole thing to unit disk. And once we put everything in the unit disk, the rest of the part just rotation, twisting stuff. Okay, so G1 maps to the unit disk, and G2 is like a shift, a translation. Phi alpha is a translation that maps alpha to 0. And the G3 is a rotation. There's a translation and a rotation. This is a translation. Well, it's not a typical translation, but it does transform alpha to 0. And this is a rotation. This is a standard rotation. All right. So this is translation in the Mobius transformation. Because translation, you will move outside of the unit disk. That's bad. So we use the translation in the Mobius sense, in the Mobius transformation. So we still keep the open disk inside open disk, but we can translate alpha to 0. And rotation will make the derivative positive. Okay, so this is a very good technical way to show that something exists, some kind of function exists. You can map some set to the unit disk. All right, so next we're going to establish 4.5. 4.5, what is 4.5? If you take the closure of F, the closure of F is going to be F union at most 0. So we're talking about the sequence, convergent sequence. So suppose we have a sequence in this family, and Fn converges to F in H of G. H of G is complete, so its image is always in H of G. And we know that you see here, Fn of 0, Fn of A is 0. Fn prime of A is greater than 0. So when you pass it to the limit, Fa is 0. This is good. But F prime of A is greater than or equal to 0. You have to add some unexpected equality. We don't want this equality. And this is the place you get 0. Okay, so you pass it, you get this. Well, let's see. We're going to discuss this situation. So let Z1 be in G, any Z1 in G, and put theta equal to F of Z1. Theta is F of Z1, and theta n is Fn of Z1. Okay, you have a sequence of images. And choose another one, Z2 in G. And of course, Z2, we say them differently, so they're let me get the charger. Okay, we have 2 points, and this is Z1, Z2, and G. And we're going to get a closed disk centered at Z2, but excluding Z1. K is a closed disk centered at Z2. Z1 does not belong to K. Z1 does not belong to K. Okay, then this Fn of Z minus psi n. Fn of Z. Fn of Z1 is psi n. Fn, remember, it's a 1-to-1. So never vanishes. On K. Since Fn is 1-to-1. Fn is 1-to-1. But Fn of Z minus psi, not psi, theta n converges to f of Z minus theta, right? This one converges to this, theta n converges to theta. Uniform, it's a compact set, so uniform. Okay. So by Hurwitz's theorem, either the limit is a constant zero function, or it has the same number of zeros of Fn of Z minus theta. Okay, that's let me get the, yeah, it's on page 152. Page 152 about the Hurwitz theorem. If you have this uniform convergence, then either they have the same number of zeros or the limit is always zero. Okay, so either Fn minus theta is constantly zero on K, or f of Z minus theta and Fn of Z minus theta n have the same number of zeros. Have the same number of zeros. All right. And the first condition, equivalently, we get either Fz is constantly theta on K, or f of Z is not equal to theta on K, because Fn of Z minus theta n never vanishes. So this never vanishes, no zero, so it's not equal to theta on K. Okay, so f of Z is a constant theta. Let's see that we have two cases. F of Z is constant theta, then f is constant function. On G. But we know that Fa is 0, so f is constant 0 on G. Okay, so from f of Z is equal to theta, we get f of Z is constant 0. If it's case 1, case 2, if f theta is not equal, f of Z is not equal to theta, we have fz2 is not equal to fz1 for z2 is not equal to z1. fz2, you see here, z2 and z1, they are different, then you will have fz1 is not equal to fz2. Why? Because this fz1 is a theta, fz2 is not equal to theta on K everywhere. So of course Z2 is inside the K. Okay, then this is f is a one-to-one function. F is a one-to-one function. Analytic one-to-one function. Remember in the last video I mentioned then f prime of z is not equal to 0 for all z inside G. Every analytic one-to-one function has non-vanishing derivative. So this implies f prime of A has to be strictly greater than 0. So we are back to this part. It has to be strictly greater than 0. Okay? So put all these things together, you see f A is 0, f prime of A is greater than 0, f is one-to-one analytic. That's it. So we get the f belongs to f. If f is not 0, then f will belong to f. And the limit belongs to the family f itself. Okay, so there's one more thing here. The author didn't emphasize, but I think it's maybe you think it is obvious, but let me point it. So f maps G into D. When we take this is a family. This is a family. F maps the region into D. What happens if we pass it to the limit? It is still inside the D, or it can take the closure. Which means, will it be possible that f maps G on the boundary point? The answer is no, it cannot contain any boundary point. Remember, f is analytic function. Fg is open. Fg is open. It cannot touch any boundary point. It has to be inside the interior point. So this situation can never happen for the analytic function. So f of g must be contained in the D, not touching the boundary. Not touching the boundary. Here, you see why I mentioned this. Fn prime of A is always greater than 0, and ups value of Fn of Z is always less than 1. But when you pass it to the limit, you actually have less than or equal to 1. But this equal sign, this equality never happens just because you are talking about analytic functions. Alright, you're talking about analytic functions. Okay, good. So we set up 4.5. We have 4.4, 4.5, and we already showed that they are enough to prove the theorem. So we are done about the proof 4.3 lemma. And this lemma is equivalent to the original Riemann mapping theorem. Good? Okay, so after that, we have our corollary. The corollary is this. Among the simply connected regions, there are only two equivalence classes. One consisting of C alone because of the Liouville theorem, and the other containing all the proper means not equal to C, proper simply connected regions. Why? Because every simply connected, proper simply connected regions is equivalent to the unit disk. So they all equivalent to one model, then all of them are equivalent to each other, right? So that's stuff. Okay, so this is a very short section, but this section contains many information and also some techniques. And you should learn something first. Analytic function or analytic one-to-one functions has non-vanishing derivative. You should be able to prove it by yourself. And second, you know that every analytic one-to-one function has analytic image. Any analytic one-to-one function has analytic inverse. Okay, that was done also. And also you need to show that a simply connected region, every non-vanishing functions, analytic function has analytic square root, right? So you have several small parts which are very useful in other places. So I try to emphasize, you need to know how to show them. They may appear in the exam. Okay? Okay, we finished this video and we will start a new section in the next video, Weierstrass factorization theorem. Thank you.